In the previous videos, we have learned to measure single qubits and multiple qubits using standard bases. However, in quantum computing, we can measure qubits in any orthonormal basis. So that's the subject of this video, that how to measure qubits in non-standard orthonormal basis. To that end, in this video, I will first explain what we meant by standard bases, and then what are orthonormal bases, and then I will write the formula that help us to express qubits in any orthonormal basis of our desire. And finally, to understand everything clearly, we will do multiple examples. So let's start. Standard basis is a set of linearly independent vectors where each vector has exactly one in it, where rest of the elements of that vector are all zeros. In two-dimensional, our standard basis will be a vector 1 0 and a vector 0 1, because each of those vectors has exactly one in it and rest of the entries of each vector are all zeros. So this represents a standard basis in two dimension. We can obviously write this standard basis in bracket notation as ket 0 and ket 1. Similarly, in three dimension, our standard basis will be so this is our standard basis in three dimension, but we will not use it in quantum computing, because in quantum computing we are only interested in standard bases which are in the power of 2. So that we will not use in quantum computing. However, in quantum computing we use 4D standard basis or 8D standard basis. So in 4D our standard basis is ket 0 0, ket 0 1, ket 1 0 and ket 1 1, because each of those vectors has exactly 1 1 in it. So I hope that you will be able to understand the concept of standard basis. So this is our standard basis in 2D and this is our standard basis in 4D. Now what about the orthonormal basis? As you have guessed already, that orthonormal is composed of two different words. One is orthogonal and second is normalized. That means this basis must have orthogonal vectors which are also normalized. Let's learn what we meant by that. A vector is called normal if its magnitude is equals to 1. That means that vector is a unit vector. Then a pair of vectors are called orthonormal if they are perpendicular with each other. So let's take an example. This is the example that we'll be using in this video again and again. In our example, we are given two vectors cat plus and cat minus, and we have to verify if these vectors makes orthonormal basis or not. I have selected these vectors because after standard basis, this basis is most widely used in quantum computing. We refer to this basis as Hadamard basis. Anyway, cat plus is defined as cat 0 plus cat 1 divided by square root of 2, and cat minus is defined as cat 0 minus cat 1 divided by square root of 2. First, we have to verify if these two vectors are unit vectors or normalized. To that end, we have to see if the norm of cat plus is equals to 1 or not. To compute norm, we can compute the inner product of cat plus with itself and takes square root. So let's do that, and this will be equal to bra plus, that will be equal to bra 0 plus bra 1 divided by square root of 2 times cat plus, that is equals to cat 0 plus cat 1 divided by square root of 2, and we solve it further, so we will get 1 over 2. Let's take 1 over 2 out, and then I will get inside bra 0 cat 0 plus bra 0 cat 1 plus bra 1 cat 0 plus bra 1 cat 1, and we know from one of our last videos that this is equals to 1, we know that this is equals to 0, we also know that this is equals to 0, and finally this is equals to 1. So our result will be 1 over 2 times 2, and that is equals to 1. So yes, cat plus is indeed a unit vector. Similarly, we can verify, and I leave it on you, that cat minus is also a unit vector. That means that norm of cat minus is equals to 1. Please do that yourself. In order to verify that cat plus and cat minus makes orthonormal basis, we have to verify that each vector is a unit vector, that we have done here. Secondly, we have to verify that these two vectors are orthogonal with each other. To that end, we have to compute inner product of these two vectors, and if they are orthogonal, then the inner product will be equals to 0. Let's compute it. So first I have to write bra plus, which is equals to bra 0 plus bra 1 divided by square root of 2. Now I have to write cat minus, and that is equals to cat 0 minus cat 1 divided by square root of 2. Now I have to simplify it. This square root of 2 times square root of 2 becomes 1 over 2. I take this out as common. Now I multiply bra 0 with cat 0. I will get bra 0 times cat 0. Then I will get minus bra 0 and ket 1, and then I will get plus bra 1 ket 0, and finally I will get minus bra 1 ket 1. And I know that this is equals to 1, this is equals to 0, this is equals to 0, and this is equals to 1. So this one and this one will cancel with each other. So inside I will get all zeros. So my answer is 1 over 2 times 0, and that is equals to 0. So yes, the inner product of these two vectors is indeed equals to 0. That means these vectors are orthogonal. And hence we have shown that this basis, which we call Hadamard basis, is indeed an orthonormal basis. This is most widely used basis other than standard basis. Now let me clear the board, and then we will do some examples to make our concepts crystal clear. While clearing the board, I just realized that I have made a mistake, and the mistake is that here I should have square root, and similarly here I should have square root. So our result will remain equals to 1. So because the square root of 1 is equals to 1, but yeah, I missed my square root here. Now I can clear the board. So the board is cleared, and now first I will write a formula. That formula you can use to write any vector in the orthonormal basis of your liking, and then we will do some examples. Let's say I have given an orthonormal basis of ket alpha and ket beta, and I want to express my qubit, that is in some other basis, any other basis, in this orthonormal basis. And let's say my qubit that I want to express in this basis is ket psi. So the formula is that ket psi in this basis is equals to dot product of ket psi with ket alpha times ket alpha plus dot product of ket psi with ket beta times ket beta. So that's my formula is, and we know that this here will be a number, and we can say this will be the amplitude of ket alpha, and we know this will be a number, so we say this is amplitude of ket beta. And because we have to measure in the basis of ket alpha and ket beta, it implies that to find the probability of measuring ket alpha, we have to scale this. So probability of measuring ket alpha is equals to square of this. Similarly, probability of measuring beta is square of this amplitude. So probability of measuring beta is equals to square of this number, and that's pretty much is how we can measure our qubits in any other orthonormal basis and measure them in those bases which might not be standard basis. So let's do some examples to make it crystal clear. In the first example, we are given a qubit ket psi which is equals to ket 0, and I have to measure this qubit in standard basis and also in Hadamard basis. So let's first measure in standard basis. By the way, standard basis is also orthonormal basis, so we can use the same formula in it also. Because this qubit is already expressed in standard basis, so I can simply take the square of amplitudes to find probability. The probability of measuring 0 is equals to square of amplitude, which is 1. So we know that 1 square is equals to 1. So we measure 0 with 1 probability. Similarly, probability of measuring 1 is equals to 0 because the amplitude of ket1 is equals to 0. Now we have to measure the same qubit in Hadamard basis. We know that Hadamard basis has ket plus and ket minus. We can express ket psi in Hadamard basis and then take the square of amplitude to find probability of measuring ket plus and ket minus. Or instead of first expressing ket psi in Hadamard basis, we can directly find probabilities using these formulas. So let's directly find probabilities using these formulas. So probability of measuring ket plus is equals to our dot product of ket psi with ket plus and square of that. Recall that ket plus is equals to ket 0 plus ket 1 divided by square root of 2, and ket minus is equals to ket 0 minus ket 1 divided by square root of 2. So let's compute this dot product and then we square the dot product. We have to write bra psi and multiply with ket plus. So our bra psi is equals to bra 0 times, and our ket psi is equals to ket 0 plus ket 1 divided by square root of 2. Multiplying them together, we will get bra 0 ket 0 divided by square root of 2 and plus bra 0 ket 1 divided by square root of 2. We know that this will be equals to 0 and this will be equals to 1. So from here we get our final result of 1 over square root of 2. But we also have to take square of our result. So let's take square of our result of 1 over square root of 2. So our answer will be 1 over 2. So in this case, probability of measuring ket plus is equals to 1 over 2. And we can easily find probability of measuring ket minus, which will be 1 minus 1 over 2. And that will also be equals to 1 over 2. So to measuring probability of ket minus is equals to 1 minus 1 over 2, which is also equals to 1 over 2. So you can see that the result of measuring ket psi in standard basis is much different as compared to result of measuring ket psi in Hadamard basis. Let's do another example to make it even more clear. Here is our second example. In this example, we are given a qubit which is already expressed in Hadamard basis, but we are asked to measure this qubit in the Hadamard basis as well as in the standard basis. So let's start. First, we measure this qubit in the Hadamard basis. To that end, we only have to compute square of this term to find probability of measuring ket plus. And similarly, we can take square of this term to find probability of measuring ket minus. So our probability of measuring ket plus is equals to square of 1 over square root of 6 minus 1 over square root of 3. And this is equal to 1 over 6 plus 1 over 3 minus 2 over square root of 6 times square root of 3. And this simplifies to 1 over 6 plus 1 over 3 minus square root of 2 over 3, and which further simplifies to 1 plus 2 minus 2 times square root of 2 equals to 3 minus 2 times square root of 2 over 6. So that is our probability of measuring ket plus. To find probability of measuring ket minus, we can simply subtract this term from 1. So 1 minus this term will give us probability of measuring ket minus. So probability of measuring ket minus is equals to 1 minus probability of measuring ket plus, and that will be equals to 3 plus 2 times square root of 2 over 6. So now we are able to successfully measure this qubit in Hadamard basis. Now we have to measure this qubit in standard basis. Recall that in 2D, our standard basis is composed of ket 0 and ket 1. So probability of measuring ket 0 is equals to dot product of ket psi with ket 0 and its whole square. Now let's calculate what will be the dot product of ket psi and ket 0, and then we will scale it. My bra psi ket 0 will be equals to 1 over square root of 6 minus 1 over square root of 3 times bra plus 1 over square root of 6 plus 1 over square root of 3 times bra minus, and this whole thing will be multiplied by ket 0. And this thus simplifies to 1 over square root of 6 minus 1 over square root of 3 bra plus ket 0 plus, and this simplifies to 1 over square root of 6 minus 1 over square root of 3 bra minus ket 0. Now let's calculate what will be this and what will be this. So my bra plus ket 0 is equals to bra 0 plus bra 1 divided by square root of 2 times ket 0, and this will be equals to bra 0 ket 0 plus bra1 ket 0 divided by square root of 2, and this term is equals to 1, this term is equals to 0, so my final answer will be 1 over square root of 2. So I have to put my answer here. So I replace this by 1 over square root of 2. Similarly, I have to calculate this one, so for that I change this plus with minus, and according to the definition of bra minus, there should be minus here, so I replace this plus with minus, and then I will have here instead of plus minus, but my final answer once again will be 1 over square root of 2, because this term will be equals to 1, this term will be equals to 0, so my final answer will be 1 over square root of 2. So let's replace this also with 1 over square root of 2. So 1 over square root of 2. So I have to simplify it further, so I'm just making some space here. I take 1 over square root of 2 as common, and inside I will have 1 over square root of 6 minus 1 over square root of 3 plus 1 over square root of 6, and I've done some mistake somewhere. I think this should be plus. So plus 1 over square root of 3, and then these two terms will cancel with each other, and my final answer will be 1 over square root of 2 times 2 over square root of 6, and this simplifies to square root of 4 over square root of 12, which is equals to 1 over square root of 3. So that's my final answer. Probability of measuring ket 0 is square of 1 over square root of 3. So my final answer is here 1 over 3, because if I take square of this term, I will get 1 over 3. So finally, what will be the probability of measuring ket 1? It will be equals to 1 minus 1 over 3, and that will be equals to 2 over 3. So probability of measuring ket 1 is equals to 1 minus 1 over 3 is equals to 2 over 3. And that's it. So I hope that everything will be clear to you, and you can measure in now any orthonormal basis. If you still have some questions, then please ask those questions from me. See you in the next video.